Okay, so let's start with just a brief review of the flip-flops. Right, so we remember that the flip-flops are all built up from the SR latch, right? Pretty much everything starts at that SR latch and builds up. The most important component, though, that we end up with are the flip-flops. And it is very important to remember the types, where we have the D flip-flop, the JK flip-flop, and the T flip-flop. Now, the D is pretty simple, in that on a rising edge of a clock, it just takes whatever is on the data line D and puts it to Q after some short delay. The JK flip-flop does not have a data line. It has two inputs called J and K, and it has a truth table that determines what the output is, depending on the inputs of J and K. The T flip-flop is the special case of a JK where J and K are connected together. And if T is true, the output just toggles. It becomes not what it used to be, right? And if it's 0, it stays the same as it was. So I have posted a video that walks through figure 12-40, which is how you use the T flip-flops to build a counter. It's built up as a helpful reminder tutorial on Vivado. It's about 40 minutes long, but it will walk through basically everything we've done in VHDL as kind of a review, and then show you building T flip-flops into a counter. And it actually is kind of helpful because I did make a mistake in the test bench when I was building it, and so you actually get to see me go through the troubleshooting process as well. Okay, and at the end of the class, after we talked about these types of flip-flops, we started about the timing requirements of these flip-flops, right? And so these each have, if we recall, a setup time, a hold time, and a clock to Q. Now, setup is the amount of time that is required for the data, say, we're going to use D flip-flops as the main example. The data needs to remain valid before the clock hits. Because if the clock happens at the exact same time as we change data, we have no idea what's going to appear at Q. So it has to be set up before that. Similarly, if the clock happens and then we change it immediately after, it may or may not hold that value. So we have to have a hold time after the clock hits. And then, so these are timing requirements that you need to meet in your system. The clock to Q is a little bit different, but it's still a timing requirement. And it just says, if I have this D flip-flop, and I get a rising edge on that clock, and say Q at 0, D at 0 is, well, let's start at Q at 0. Q at time 0 is 0. And data at time 0 is 1. So it's about to change on a rising edge of the clock, right? Clock happens. That means we want 0 to transition to 1, right? That's what a D flip-flop does. Rising edge of the clock, take the input, throw it on the output. This time here that it takes it to go from 0 to 1 is the clock to Q. That is the same idea for like a JK flip-flop or a T flip-flop for how long when the clock hits to when we update the output. So this is all going to have a lot of importance when we come back to introducing what we call non-idealities, right? So an ideal flip-flop would have 0 setup time, 0 hold time, and 0 clock to Q delay. just like ideal logic gates, would have no delay through them. But when we start sticking them together, we can start having delays that can throw errors into these systems. So that's where we're heading with this ultimately, is how do we realize real systems that have these non-idealities that may interfere with each other. Let's see, which is a good one?
I've got a question on, I know this is back to where it's like last time, but
Fine.
I'm having a hard time understanding SR latches, like the timing and like, so if S is high, Q is high, like I don't know if I'm understanding it right.
So we don't have to worry very much about the timing yet of the SR latch. All right, let me flip back to where we're at there, so I can remember.
Like
Yeah.
is S, could I say R is like reset? Would R be?
Yes, that is essentially what it is. S is set it to 1, and R is reset it to 0.
Okay.
Effectively. The other way of viewing it is if you assert reset, it will set Q bar to 1. Right? But then that Q bar gets flipped back to the input of where the set is. And because you cannot assert set and reset at the same time, that will drive Q to be the opposite of Q bar. Okay. So let's draw out a little bit of a timing diagram. Okay, so we have JK clock, and then what is Q doing? And we're going to start Q low. Okay, so if we look at this, and the JK flip-flop truth table is back on which page? Just so I can tell you guys where to look. I'll just write it here, where I have J, K, and Q, n plus 1. Right, so this is saying what my JK inputs are. What is the next Q? So after the next rising edge of the clock happens, what happened? What is the next Q? Well, if we're both zeros, it stays the same. If it's just K, we go to 0. Just J, we set it to 1. And 2 1s, we toggle. Q goes to Q bar. So that's our JK flip-flop. So we care mostly, right? The most important thing on this diagram, where are the important points on this timing diagram? The rising edge of these clocks. So other than those, Q will never change, right? So this is always your first step, is identify the important locations in your timing diagram. right? At first, this might look bad, right? Because we're changing the clock and K at the same time, but it's a falling edge. This is rising edge triggered, we don't care. So at our important points, we come along and we're going to evaluate what are J and K right now. Well, K is 1, J is 1, so what does Q do? Yes, not Q, it flips to 1. And it stays 1 regardless of what J and K are doing all the way until the next point of interest. Now again, we evaluate. J is 0, K is 1. J is 0, K is 1. We're now setting it to 0. Ta-da. So that's our basic ideal timing diagram for the JK flip-flop. But there's this interesting issue of this clock happens, and then it actually takes some time for it to update. So we would draw it like so. Actually, let me change color so it's a little more apparent, and I will make it a little bit steeper. Where I'm going to give it a bit of an edge, right? But more than that is it may not even start here, so we're going to have something that looks a little bit like so. Because we don't know. There's some delay, and you will have oftentimes a maximum and minimum given. So we can go further and say, well, what if this is time 0, this is 20 nanoseconds, 40 nano, 60 nano, right? And I say that my clock to Q delay is 10 nanoseconds. Maximum, let's say. Let's say my max clock to Q is 10 nanoseconds. And I'm going to do that on a new Q line. So I come along at 0. This happens. We change from 0 to 1. We already know that. But the clock to Q is 10 nanoseconds. So that doesn't happen until here. Right? So this red line is the visualization versus the blue line of clock to Q. That's our delay. Are we good if I erase this? Okay, so a real world application of these D flip-flops that is very common is you're going to have a flip-flop, D, Q, and you want to remember what it has done and make a decision based on the previous, what we will call, state. So Q here is the present state. So I'm going to label that as S for state. And more specifically, I'm going to label it Sn. What comes into the D is Sn plus 1. Because once the clock happens, that will be the next state. But we've been building all of these combinational logic devices that can make decisions, right, and create an output based on input. So let's just draw a generic block and just call it some combinational logic, right? This is AND gates, OR gates, that kind of thing. Its output goes into the D input. Its decision is put as the input to the flip-flop. It's going to have, potentially in this case, two inputs. It's going to have what was our last decision and some data feeding into it, right? So now I can make a decision of what comes next based on what happened before, right? There is going to be a delay from D to Q, and there's going to be delays through that combinational logic. So ultimately, in order for this decision to be made correctly without having an error or a glitch, we need to satisfy this statement. The book uses slightly different notation, but I'm sure you can puzzle out how these met together. Or the clock period, it's not frequency, the clock period has to be greater than the time for the, and this is, I should actually rewrite this to be a little bit more differentiated because, so capital T is generally used as period and lowercase t is used as time. So the clock period has to be greater than the sum of the clock to Q, the delay through the logic, and the setup time. Because the setup time comes from the idea that it needs to be ready some amount of time prior to the next clock. So this is the maximum amount of time that we can have in all of our delays. That's D to Q through the combinational and then the required setup at D. If we violate that, we have no idea what the system is going to do. So to help contextualize this, one of the examples that I really like is the stoplight. This is the fundamental building block toward what we would call a state machine. State machines are all around us. They're used prolifically in digital logic, and they are probably the most important concept for all of digital logic. Now, the way it works is, let's say we are at a red light. So that means the output here is red, right? We would actually need two of these, right? Because if there are three states, red, green, yellow, then I need 2 bits. Right now I'm only storing 1. But we can remember that we can do this and say now it's 2 bits wide, right? So now I can say the output SN, the current state is red. That feeds back to here. Under what conditions if we're red? So the question that this combinational logic is asking, much like your key example that we did before, right, is if we are currently red and we have some sort of input, what do? Well, if data in is nothing, we stay in red, next state stays red, we update to red and we sit there. What data in might trigger us to go out of red? Well, we could have something like a light sensor. So it's a nighttime, car pulls up, it detects light, this asserts 1, and says, oh, if I am red and there's a light sensor on, I surely need to transition to green. So the combinational output is going to say your next state should be green. The clock hits, green gets put out, goes back to this combinational logic and waits for the inputs to tell it when to leave that green state. We will cover this more in much more depth. This is what I'm doing is introducing the idea, and we'll come back to it in later lectures at great depth. But I want this idea stuck in your head so that it is less confusing as we move forward. There, we're going to take a pause on the the sequential logic, and move on to some of the ideas that we can build up other than state machines using D flip-flops. One of the most important is simply called, and I mentioned this last time, called the register. The register is just a series of D flip-flops that are used as memory, right? So if you had some 8-bit number that you wanted to store to add to something later, you would store it in a register, which was just a series of D flip-flops, which we could represent like so, right? This is now an 8-bit register. I'm storing 8 bits to use later. But what happens if I want to use more and more and more memory, right? This starts outputting tons and tons of wired connections everywhere. We are realistically limited to a finite number of wires that we can have running around. The more wires we have, the more room it takes on one of our devices. So this is where a new concept comes in that we call addressable memory. The idea of addressable memory is it's just a big block of storage like a neighborhood. And if I send a message to a house, I need its address. What I get back is not the address of the house, but it's the contents of the house. So it'd be like saying, I want to meet with somebody in this neighborhood, so I'm going to send a message to their address saying, I want to meet with you, and they will come to me, right? So that's what this address is doing. It's saying, in the memory block, there's a giant amount of you, and I want to send you a message saying, come on out. So we'll have an input called address and an output called data. That's addressable memory. Now, memory, right, we're familiar with it from things like our computers, right? It can come in the shape of ROM or RAM, right? Those are the two of the common ones you probably hear. ROM being read-only memory. And I apologize, there is not a section in this book for this, I don't believe, but it's an important idea. So the next one, ROM, read-only memory, and RAM, random access memory. RAM, the random access basically meaning you can access any part of it, more or less. So the ideal memory needs to have, well, the ideal memory would have a couple of qualities. The first off being zero latency, meaning as soon as I ask it for the data, it would give it to me. I give it the address, instantly get the memory. We know that's not true because there's delays, right? But that would be ideal. The next is it would have infinite amounts of storage, right? We don't like running out of memory. It causes us issues. It would be free. That'd be great. And it would have infinite bandwidth. So in the case of an 8-bit register, I can access all 8 bits at the same time. In a ROM, for example, if I send it the address, I can only access those particular address bits at once. I don't have unlimited access to them. Then it would also take no room on your board, right? Because if you want to store stuff and it's infinitely large, but it takes a physical amount of space, suddenly your board would be infinitely large. So ideally, it would be infinitely small for each component. Unfortunately, each of these are trade-offs. We have to make design decisions based around them. So if you make it bigger, it gets slower. If you want to make it faster, it costs more money because the way you make it faster is by using more expensive manufacturing processes and making your devices smaller and faster. Also, the higher bandwidth, the more things you can access at once, costs more money, and takes up more board space because there's more wires and more logic in order to control that. So those are some of our major trade-offs that we're looking at that. So in order to kind of realize how it's storing this data, most of you have taken or are in 1270. What device do we have that can actually store electricity? The capacitor. So if I take a capacitor, so here on this side, this is called our bit line. So it's carrying data for us. This is a transistor that functions as a switch. When I raise this switch to enable, it turns on, allowing whatever else on the bit line to either be stored in or read out of this capacitor. That makes sense, right? This is one of the simplest ways that you could store a bit. One of the challenges being it's very fleeting. If you turn the power off on the device, it just goes away after a fairly short amount of time. So this is one implementation of what we would call DRAM, dynamic RAM. We can make it better and have what's called SRAM. It gets more expensive because it takes more devices, but is useful. I'll erase this one. I feel like I forgot something. No, that's fine. Okay, so here we're using two inverters. We turn on the enable, and it allows bit and bit bar to read in or read out from that. More expensive, but has some benefits. I'm not going to go too deep into the architectures of memories at this level. They don't get, I don't know, they're understandable as you get slightly more advanced, but they're not really what's important to this. It's just a little bit important to understand where it's coming from, how it's being stored. But at the bigger level, when we start stitching these elements together, we're going to have some big block of memory. Right? And it's going to be what we would call a two-dimensional array of memory. So it's going to have rows and columns of memory. And I know that I need to send an address to it, right, to read this out, right? So inside of it, it's going to have rows and columns, and we want to be able to access those rows and columns. One way of doing this is I feed the address into this decoder. And actually, I'm going to back off a little bit. I take address, and this is stored in some register, right? And it's going to send its most significant bits off to the rows of this memory. Similar, we're going to have a column decoder. And this address register will send its least significant bits to this column decoder. So we say, which row do we activate and which column do I take? And I could take multiple columns, right? Especially if you think of each of these as one bit. I'm going to have a word length, which is how long this is. How many do I take out at one time? So this might be an 8-bit word. So you will hear terms of, shoot, I forgot the exact one. It's byte and word addressable. Byte addressable and word addressable. Now, byte addressable means that you can access any byte within the memory. Word addressable means that you can access only word level. So if your word is 32 bits, you have to read out that whole word. You can't access just that one byte. Byte addressable is that it has the memory for both word or byte level access. And you will see these when you buy data sheets, that you'll be able to send it a command and either get a byte or a word. So say we want to do this, right? I just said, the bigger we make this, the slower it gets, right? So if we want the benefits of both fast and large, what might we do? We start combining them. We start having layered memory. So instead of just having one big one, we're going to start having a big one that reads into something faster, that reads into something faster. Now, this is not something we'll address in this course, but it is a helpful thing to be aware of, especially as you kind of start exploring your own projects and maybe encountering some issues as you program in other courses. This is where the terminology of, if you're looking at buying like a computer, like a processor, it'll have like amounts of L1 cache and L2 cache and L3 cache. Those are all stacked memories that are designed to take from big memory and make it faster and faster and faster. So we start preloading stuff out of the big memory, like say a hard drive, and preparing it for something really fast, like your RAM stick in a computer. So we build up layered memories. The fastest memory we have is just registers, because we have complete access to everything in it all the time. Okay. That is memories. I'll take a moment. Does anyone have any questions on flip-flops or memories?
I got a question on flip-flops. What does latch mean when something is latched? Like in the book it says, like with the SR flip-flop, if both inputs are 0, then it's latched.
Yeah, so latched just means hold on to, right? So you might hear the term like barnacles are latched onto the boat, right? In this term, it doesn't mean anything different. It just means we've latched onto whatever value there is. It doesn't want to let it go unless there is some physical disruption.
So what it means, like this truth table, like S is 0, R is 0, and then Q and Q naught are latched, so they're just what they were previous. Yeah.
Yes.
And then metastable means that it can't really know what they're going to be.
Yes, metastable is in this in-between flux, and we don't know where it's going to end up. So done that. Okay, so the next thing that I'm going to do, we've talked about it in the lab, but it's going to be good to have it on video for anybody that is not able to attend lab, and it's probably worth recovering, right? So in lab, this week's lab, or last week's, Monday's lab, was all about actually taking logic that you've designed and putting it into a real board and having it do something, right? So you'll notice that we went through these processes, and one of them is synthesis, and one of them is implementation. So each of these have important roles in taking what you've coded and turning it into real world hardware, right? So we're not writing a standard programming language when we're writing VHDL. We're writing a hardware description language. We're using code to describe what hardware is. Synthesis and implementation are the process of taking that code and first turning it into logic, which is what synthesis is, turning it into the circuits. And then implementation is specifying it for your target. So VHDL can be written to write to like an FPGA, like we did, or it can even be used to write what we would call an ASIC, an application-specific integrated circuit. So an ASIC is something that you would make, and then at great cost, you would send it off to a fabrication facility, and they would build it for you. And that's like what goes inside of those little black packages that we use, right? Is those ASICs. Okay, so in 3610, the following course of this, we cover that in more detail. What does synthesis do? What does implementation do, right? But for now, let me see if I can't pull up Vivado. Great. Oh, come on. And I got to change this over to screen sharing. Okay, so we're all familiar with Vivado by this point, right? And here's the code that I pulled up. This is the video that I walked through that uses T flip-flops to build into a 4-bit counter with the test bench. So when I want to turn this into something useful, right, I need to run synthesis, run implementation, and then generate the bit stream. So I'm going to have a little bit of an error here, I think, if I do it.
So when we did the lab, I just went straight to generate bitstream.
Yes, so clicking generate bitstream will, or even generate implementation, whichever one you click, will send you that little pop-up message that says, synthesis is not ready. Should we go ahead and run that? And then you'll just click OK. So generate bitstream will run all of that for you in order to get to the point where it generates bitstream. It is possible to accidentally click generate bitstream, and if you click the wrong buttons, because synthesis say isn't ready, it will pull the old synthesis. And so you may have thought you updated it, but you didn't allow synthesis to rerun, and then you can cause it to have problems. So that is something to be aware of when you generate bitstream.
So you're saying, like, if you generate bitstream and then your board doesn't work right, and then you go back and edit your code,
yeah,
you could generate bitstream again, there's a possibility that it might not have run synthesis.
Oh, yes, but only if you don't click OK to rerunning synthesis, because it will pop up with that little window asking you, right? So it takes a little while to run. You can notice that up here in the top right, it has a little swirling icon. That allows you to know that it is in fact running.
So right now, are you just doing synthesis or implementation?
I told it to run implementation. So part of the issue with FPGAs is that they have to be told what is happening to them on the outside world. So on your basis board that you guys used in lab, it has switches that are hardwired up to some of the pins. But the FPGA has no way of knowing that that's what's there. You just tell it that it's either an input or an output. The way we do this is through the top level ports. So if I go ahead and I'm going to click OK on this for 1 second because we're going to come back to it. Look at my top level. These ports, CE, clock, reset, and count, are all going to be outputs to the real world, if it's the top, right? So for an internal module, it can just be connections internally between modules inside the FPGA. We've dealt with that repeatedly. If it's your top level module, that is what's expanding out to the physical pins. And that's where that constraints file came in. That example that I gave you is to tell it what pin does this port attach to.
So it's all top level is what goes to your constraints.
Yes.
Top level ports go to your constraints.
Yes.
But you also need the other things in your constraints, like the clock. You know how we had that one?
Yes.
W5.
So the clock, in this case and in many FPGAs, is actually physically tied to a pin.
So you don't have to worry about that. But
So
you do.
So to get the clock, I tie it to W5 in our case, because W5 is a 100 megahertz clock. Now that can happen one of two ways. Let me take a drink. One is it could just be hardwired to an internal oscillator that is making the clock, and it's outputting it there to make it easy for you to access. The other way is some of the FPGAs will require, many in fact, will require an external oscillator in order to have a clock. So it would actually be an input pin provided to the FPGA. So then you have to specify that in order to use a clock, we need to take it from outside in the real world. Because we use what are called crystal oscillators for most of our good clocks. We actually use crystals to make good clocks. And then we use something called a PLL, or a phase locked loop, in order to use that, a good clock, to generate higher or lower frequencies. So once I've run synthesis, you notice that I can pop up various options on the side, where I could launch a constraints wizard to help me take care of that constraint. I don't generally use these, and I'm not actually sure I've clicked it in Vivado. That's funny. But it will, I'm sure you can find a tutorial to go walk through the constraints wizard if you'd ever like to. You can have to set up something called Debug. And what Debug would do is it actually allows you to view internal signals to the FPGA on your computer. So it sets up a little processor inside the FPGA with little probes that'll go out and detect signals, and then you can just capture moments in time to see what is actually happening on your FPGA. Because unfortunately for us, just because something simulates and synthesizes does not mean it will work. So we have to be careful when we're making that transition to synthesis and being aware that not every code line we write can be synthesized. Okay. Inside of implementation, and there are a lot of others actually in synthesis. So it can actually give you things like power consumption. It can help you estimate the amount of power that you're going to be consuming, right? We have a bunch of tools inside of synthesis. Inside of implementation, we have the ability to start running some of those similar reports like noise, utilization, power. This is a report of how it actually happened. So the synthesized version is of what we think will happen. The implementation is, this is literally how it's going to be put down onto your board. Inside of that, we have the device window that looks like so. And you can literally come in here and using the nets on this side, I can open them up and come in here and say this count OBUF is actually right here. I can literally see where they put it on the chip. And it can tell you how much of the chip did you fill up, how many. So the FPGAs will have actual what we call built-in multipliers. So if you say, I want to multiply A by B, it will just go to the multiplying cores and use one of those. And you can see how many of those you have left. So there are finite amounts of resources, and this can help you allocate them to make sure that you did it. And if you've made something too big, you may need to start thinking about logic simplification or buying a bigger FPGA.
So there was something that you said, if you made it a test bench and you had like a for loop or something, you could possibly fill up your FPGA with a bunch of.
Yes. So, and that's not in the test bench, that's in any of your modules.
Oh, okay.
So the issue is that when you write a for loop, it is either what we call unwrappable or not. An unwrappable for loop is essentially a for loop where each iteration does not depend on the previous input. If it is not unwrappable, so like if loop 2 requires an output value from loop 1, it's not unwrappable, the FPGA isn't going to implement that in parallel logic. It's going to implement it as a cascade of logic that is just waiting, similar to like a ripple adder. And if your loop goes for 100 or 1,000 or 10,000 iterations, which is not uncommon, you can get into some serious trouble.
You can just fill your FPGA with a bunch of.
With that same block over and over and over and over again.
And use up a bunch of resources, I guess.
Yes. And as we go along, the tools get better and better at doing this, though. So it used to be kind of that it was a huge danger writing for loops. There was also another issue. So let's go open up the T flip-flop. And so, oh, not the T flip. Let's open the 4-bit counter. So my signals say count temp, right? That's where I'm holding my counted value. We can write a starting value for it by doing this, right? So this is saying that count temp is going to start at 0. Now in my 3610 class, we'll talk about synthesizable versus non-synthesizable logic, and I will harp on the fact that this is not synthesizable. Just because I tell it to start at zeros does not mean it will. This used to be essentially universally true. However, many modern FPGA technologies will be able to synthesize this. Not all of them. And ASIC technology, if you're designing chips for like VLSI courses, for example, will not synthesize still to this day. So I actually had this question on an exam that I just gave to my 3610 students, and I asked them the question on, how did I ask it? I gave them code basically like this, and I asked them, which of these lines is most likely to cause you a problem in synthesis if you are not aware of the target technology, right? So these are some like advanced ideas. It's okay if it doesn't settle in. I like to kind of introduce some of them and then we'll circle back around to it, right? Kind of repeating helps it stick. Okay. So that's implementation, synthesis and implementation. Next, we have the generate, bitstream, and debug. So let's not worry too much about the debug. I don't think we'll use it in this course. We do use it in 3610. The generate bitstream is literally just a stream of ones and zeros that are going to get written to the board. Now, there are actually 2 ways of doing this. And Oh, it's not happy with that. Okay, so the first way is the way we did in class, where you wrote the bitstream and it programmed the board. But you'd notice if you turn the board off and turn the board back on, it's back to its default state. It is possible, and I don't do it in this class or the other one because it's inconvenient to me, but it is possible to write it into a memory that it automatically boots from on power up.
On the board?
On the board.
I thought that when you programmed the FPGA, it physically programmed it inside of the FPGA.
It does. So that's what the bitstream is doing, is making physical connections between blocks of logic.
Right.
But they are temporary connections.
Oh.
As soon as the power goes away, they go away.
Oh.
But we can write to a memory that is used on boot up to automatically string those connections back to it. This is useful if you say design a product that may, run out of batteries. You don't want to have them have Vivado and be able to plug it in and reboot the FPGA. That is not really a good product, right? So what you do is you save it into a memory that then on boot up, it automatically saves in there.
So are there FPGAs like the old FPGAs that once you programmed it, it's like hard programmed, like you can't change it? Like that's how it is for the rest of...
Yes-ish. They were not called FPGAs.
No.
And these ones, they would use a technology called anti-fuse technology, which is where a fuse is something that breaks when it gets too much electricity. The anti-fuse is something that sticks together permanently when you stimulate it.
Okay.
So yes, there are physical ones that do that. That they're not very common anymore, and you'll hear them referred to generally as PLDs, programmable logic devices.
Maybe that's what it was that I was thinking of.
Yeah.
Because in high school we did something like that where we programmed it like that, and there was like some complicated way of erasing it and programming it again or something.
Yes. So the next evolutionary step after the anti-fuse technology was a technology that would be mostly permanent and was only erasable by UV light. So you'd open up the thing and shine some lights on it, and that would erase it.
But now the newer technology is you have an FPGA that on boot up, the memory will program it.
Yes.
Like what you were saying.
Yeah, but realistically, there are still what we call CPLDs, complex PLDs, that are also reprogrammable. They're less user-friendly to reprogram, that do retain their information on power down. These tend to be smaller, less customizable, and much cheaper. And you will encounter them in industry if you ever go into manufacturing design. If you're building like industrial machines, CPLDs are prolific. Yes, so I clicked the generate bitstream. It failed because I have not created a constraints file. So it has no idea how to assign pins to things. The implementation doesn't necessarily care, but the bitstream does. Once I've done it, you'll notice down here in the window, I have things like the power window, and it will estimate how much power it's going to take. And not only that, where is the power being consumed? And we have two ideas of power. We have static and dynamic. Static being how much power do we consume if we're not doing anything, and dynamic is what's our estimated if we're being active.
So it says it's taking almost 2 watts of power. Is that what it's saying?
Yeah.
Is that a lot of power?
A ton.
Yeah, isn't that?
Yes. FPGAs in general are not very power efficient. That is one of their major downsides. So you will use FPGAs very often to demonstrate an idea is feasible, and then you will actually build it into an ASIC. That's very common to do, just because ASICs cost a lot of money to make. FPGAs are very cheap, but FPGAs have lots of downsides. So yeah, we're using 2 watts just to count. That's fairly ridiculous. We should roughly be using pico watts.
Right. I thought it was going to be like milliwatts or something lower like that.
Yeah, no, so in modern like technologies, if I'm talking like about streaming data, they're measured in picowatts per bit. Is like a real target. And it's like single digits now for some of this, for some of the most advanced technologies. Let me check my notes and see if there's anything else I wanted to cover today. No, it looks like actually we're done 15 minutes early, which is not too bad. We do have an exam a week from today. Don't forget it. The way it will work, and I'll send out an announcement so that we're clear, is you can take it from anywhere. It will be open book, open notes, open everything except for another person. So you can't post questions to Chegg or Course Hero or Stack Overflow or any of those. You can't ask your friends, but any existing internet content is allowable. It will be taken during class time. You will, if you are here, if you can come to class, I will hand out to you an exam and you can just hand that back in. If you don't come to class, you will need to be comfortable turning a Word document for PDF. I will provide both Word and PDF documents on Canvas. You will need to be able to turn those back into a PDF and submit it. So make sure that you are comfortable making that transition. The reason I'm doing this is because COVID is kind of blowing up now, if you haven't noticed. And I don't want you to feel pressured to come in or like that you'll be at a disadvantage if you're not here or any of that. So and I don't want you to feel like you're disadvantaged if you come as opposed to not. So it's open everything. I do monitor a dozen-ish of the homework help websites for cheating, and you would be shocked at how many wrong answers you get. If you get an answer, catch you cheating, you fail the exam. You fail the exam, it's highly unlikely you'll pass the class. You get reported to the administration people. You do that twice, you get kicked out. No one wants to get kicked out. It's not worth cheating. You guys are actually all doing really pretty well. Remember that a 4.0 is not super important. I recommend trying to get better than a 3.0 in your GPA, and it's best to get over 3.3, but after that, it really doesn't matter. They care more about how articulate you are in your interviews, what projects have you worked on, that kind of thing. So don't fret about every percentage point, and don't cheat because it's not worth risking your future.
What stuff is going to be on the, like what can we study?
So for now, focus, I haven't written the exam yet. So for now, focus on the homeworks that we have done since the last exam. So if you look at the class schedule, it says the first exam, yeah, so it says the first exam was through some date, and this exam will say through some date. Content from the previous exam is fair game, but it will not be the focus of the questions. So I may ask you to use a K-map to do something. One thing I will specifically tell you, there will be no VEMs, the variable entered maps, on this exam. I barely covered them. They're not that important. You'll be fine. They won't be on there. There may be 4 variable K-maps, right? That is a fair question. There will be lots of questions about VHDL, and I may ask you to handwrite some VHDL as best as you can. Any questions that are about sequential logic are going to be fairly simple because we've just started that, right? So most of it is going to be on combinational logic as it's used in VHDL.
So like the ALU and the
Yes.
other adders that
Yes.
were created.
I very likely will provide you with VHDL code that has some errors in it and ask you to spot and correct the errors. That is almost a certainty.
And you said it's timed? Is it timed?
It will be timed. It'll be an hour and 15 minutes, as is our class, with 15 minutes extra to make sure you get it turned in. So I recognize that students that are not taking it in this classroom will use that 15 extra minutes to try and do some more work. So the way that I do it is I watch for those that are doing it online to start submitting. Once they've started submitting, about half of those that are doing it remotely, then I will have the people that are present turn it in. So that whether you're here or not, you get the same amount of time. If you are not here and you take it remotely, don't abuse that 15-minute window to submit it too much, because if you miss that window, you get 0. Make sure you're comfortable turning things into a PDF and submitting it, because it will only accept PDF submissions on this.
Can we picture convert PDF?
Yes, as long as it's a clear, clean, readable PDF. If it's not readable, no points. Write cleanly, neatly, clearly.
Because sometimes typing everything takes more time.
Yeah. So if you're worried about the PDF, try and come in. Again, if you can't make it, it's not the end of the world. I will be responsive to emails and Canvas messages during the exam, so that if you have clarification questions, I will answer them. Or if you're having help or you're needing help with the submission, make sure you tell me that you have a problem prior to submitting the exam. If you have a problem taking the exam, like you end up in the hospital, tell me before the exam. I will be understanding if you get hit by a car or something and it's very sudden and you have no warning. But something like, say, COVID, you generally have warning before you go to the hospital. Send me a message. Tell a friend to send me a message, something, so that I know beforehand. I recommend sending me a message on Canvas if you intend on taking it online, just so that I'm aware of how many people are going to be taking it remotely. However you want to take it is fine. You could just have a tablet, write on it, and submit that. You could take it, print it out, submit that. It will be an assignment called, it will be posted as an assignment called Exam 2. You will open up that assignment. It will have a list of files to download, probably just one, right? You'll download it, take the exam, turn it back into a PDF, and you'll get A's, right? Because you know everything. Yeah. If I remember correctly, I didn't have to curve the last exam. You all did very well. It was a great bell curve. Hopefully the same thing happens. If something goes weird and I write a terrible exam and the average is 50, I will curve it. It happens. So we will do a review on Monday.
Oh, good. I've got a question. I just sent you an email with the PDF of flip-flop thing that I was looking at, but they had a truth table that had, well, let me show it to you. Because I'm trying to make sense of it, and it's not. So they have this SR. So they talk about the metastable and stable.
Okay.
And they have this right here where it's like S and R, and they have Q, and Q next. And I don't get why.
Yeah, so the question is, what is the current Q? This is Qn, this is Qn plus 1 in our notation.
So Qn plus 1 means like the next.
Yeah.
Like if you switched one of those.
Yeah. So SR latches aren't clocked.
Right.
But what is going to happen after the gate? Right? So if 0, 0, we don't care what Q is, no matter what, it's going to 1, apparently, to them. Which is incorrect, actually.
Yeah, I'm not sure. It's from like
Yeah, this is an inverted SR latch, actually.
Oh yeah, because it is an and.
Yes.
Oh, okay.
So, well, more specifically, it's S naught and R naught.
Okay.
So if S is low, S is actually high. So this is saying, yeah. And this is also correct because they have the double assertion. 0, 0 should be unknown.
Right.
So this is actually really terribly incorrect in a lot of ways.
Okay, I will make a note.
The question about the clock.
Yeah, let me hit stop recording on this. And then for the video people watching, there will be a review on Monday. I will post that review as quickly as I can on Monday afterwards. If you have specific questions, make sure to email me. Oh wait, I was pointing up there, but you guys are screen shared, so sorry about that. You still heard me.